So now we take question number 7. It will make you think a little further. There is a charge of 4 into 10 to the power minus 8 coulomb distributed uniformly on the surface of a sphere of radius 1 centimeter. So you have a sphere, and this sphere has a radius of 1 centimeter, and on the surface of this sphere a charge of 4 into 10 to the power minus 8 coulomb is distributed uniformly. Now this sphere is covered by a concentric hollow conducting sphere or shell of radius 5 centimeter. So this one is covered by a shell of radius 5 centimeter. Now first part, nothing is told about how much is the charge on this. First part, find the electric field at a point 2 centimeter away from the center. So here in the first part, I have a point P here which is 2 centimeter from the center. How much is electric field at point P? So answer is clear, because there is no charge on it. It won't provide any electric field, and moreover, if it has some charge, it will not provide any electric field within its own shell, within its own surface. So if there is an electric field existing at point P, it is only due to the inner sphere or shell which is charged. And for the outside point, it will behave as though the whole charge is situated at center. So electric field at point P will be 1 by 4 pi epsilon naught small q by 2 centimeter square. I hope you will agree with me. It will act as though the whole charge small q is situated here, and it is this q charge which is providing electric field at point P. So electric field at point P will be 9 into 10 to the power 9. Charge is 4 into 10 to the power minus 8. And this separation is 2 centimeter square. So electric field at point P, you can calculate is 9 into 10 to the power 5 Newton per coulomb. So first part is done. Second part. Now we again make this arrangement for the second part, for part B. I will again start with the same arrangement. Here we are told there is inner sphere of radius 1 centimeter, and it has a charge on it which is 4 into 10 to the power minus 8 coulomb. And there is another sphere or shell of radius 5 centimeter. Now, the B part of the question says, a charge of 6 into 10 to the power minus 8 coulomb is placed on hollow sphere. So there is, we bring now a charge on this. The charge which we bring on this has a value 6 into 10 to the power minus 8 coulomb. We are bringing a charge this much onto this. Question is, find surface charge density on outer surface of the hollow sphere. So in the beginning I told you the concept of induced charge. Here, if you have a charge Q, then by induction, inside will obtain a charge minus Q, and outside will obtain a charge plus Q. So if you are looking for the outer surface, it will have a charge capital Q plus small q. So if I am looking for density on the outer surface, or charge density or total charge at outer surface, it will be Q plus Q. So capital Q is 6 into 10 to the power minus 8 and plus small q is 4 into 10 to the power minus 8. That is 10 to the power 10 into 10 to the power minus 8 coulomb. And if you are looking for the charge density on the outer surface of the outer shell, then you can say it is Q plus Q by 4 pi capital R square. But remember that this addition of induced charge from inside to inside of, from inside shell to the inside of it minus Q and outside of it plus Q won't change neither the electric field anywhere inside, neither the net potential anywhere inside. It doesn't affect. So that's why we have taken the concept of induced charge as part B, not part A. Now, in order to strengthen that concept we just discussed in the previous question, question number 8. Question number 8, the framing of question number 8 you will appreciate. Question number 8 says there is a solid conducting sphere having a charge capital Q. So you have a sphere which has a charge capital Q, and it may have a radius A. Conducting sphere. So for a conducting sphere, if I show the charge like this, it is incorrect. The charge should be on the surface only. If it is a conducting sphere, if it is a non-conducting, then charge can remain inside. So a solid conducting sphere having a charge capital Q is surrounded by uncharged concentric conducting hollow spherical shell. So this is surrounded by another shell, maybe of radius B. Let potential difference between surface of solid sphere and that of the outer surface of the hollow shell be capital V. So I look at this part. As per the question, it is mentioned that in this situation there is a potential difference which is capital V between the surface of the inner sphere and outer surface of the shell. I'll show it. On the inner one, there will be a potential 1 by 4 pi epsilon naught Q by A. And for the outer shell, it will behave as though situated at center. So for the outer shell, the potential will be 1 by 4 pi epsilon naught Q by B. For the outer, it will behave as though situated at center. So if we assume it to be at center, then for the inner it will be Q by A, for outer it will be capital Q by B. And then, as mentioned in the question, the potential difference between V inner minus V outer, which is going to be 1 by 4 pi epsilon naught Q 1 by A minus 1 by B plus 1 by B. Okay, when we are looking for the potential difference, it is 1 by A minus 1 by V. It is represented as capital V as per the question. What will be new potential difference between the two surfaces if the outer shell is given a charge minus 3Q? So in this situation, what will happen if I supply a charge minus 3Q on the outer shell? So in this situation, we are supplying a charge minus 3Q. We are supplying a charge So just imagine that in this situation, we are supplying a charge minus 3Q on the outer shell. What will be the impact? If I supply a charge minus 3Q on the outer shell, what will be new potential on inner shell and outer shell? So what will be the potential on outer shell now? It will be 1 by 4 pi epsilon naught Q by B, which is already existing due to this charge. There will be certainly a potential here. and due to its own charge, so plus minus 3q by b. It is minus 3q on radius b, so it will have its potential due to its own charge. But remember, if there is a potential v that exists here, same v will also come in. So if I now say, what is the potential going to be on inner shell now? So inner shell will be 1 by 4 pi epsilon naught q by capital Q by a, which was already existing, plus 1 by 4 pi epsilon naught minus 3q by b, which has entered on the surface, will as it is come inward. So if I look for v inner minus v outer, answer will come out same, 1 by 4 pi epsilon naught q 1 by a minus 1 by b. So if I compare equation 1 and 2, I can say v and v dash are same, no change of potential. There is no difference of potential. If the potential difference between the inner and outer was earlier v, when we introduced some charge on the outer, the potential that has added on the outer has also itself added on the inner. Thus, the potential difference between the inner and outer will remain v only. So this is question number 8 for you. Now, question number 9. A charge capital Q is distributed over two concentric hollow spheres of radius small r and capital R. So you have hollow sphere of radius small r and outer of radius capital R. A charge capital Q is distributed over them. Maybe it was having a charge Q1 and it was having a charge Q2. In fact, it is capital Q which is distributed among them as Q1 and Q2. But surface charge densities are equal. So I can say sigma 1 may be the surface charge density here, which is Q1 by 4 pi r square, and sigma 2 is the surface charge density on the outer, which is Q2 by 4 pi capital R square. But question says surface charge densities are same. It means sigma 1 is equal to sigma 2, or Q1 by 4 pi r square is equal to Q2 by 4 pi capital R square. So we have another relation which says Q1 by r square is equal to Q2 by capital R square. So the two information are with us. Capital Q is this and the other relation is like this. Find potential at common center. So we are looking for what is the potential at common center. Potential at common center means potential at O. Now there are two reasons for the potential at O. Number one, due to this charge, it will have a potential V1. Same V1 will exist here. And secondly, V2 will exist due to the charge on the outer shell, and the same V2 will exist here. So V2 will shift as it is from outer shell to this, and V1 will shift as it is from inner shell to this. So what are the two potential at the center? The two potential at the center are V1 and V2, or V inner plus V outer. Now, V inner will be 1 by 4 pi epsilon naught Q1 by small r, and V outer due to its own charge at its own surface will be 1 by 4 pi epsilon naught Q2 by capital R. So I have got these two equations which are relating Q1 and Q2. We want our answer in terms of capital Q. So how can we convert that? I use equation 2 in equation 1 equation 2, this can be equation 3. So 2 in 1. So if I use 2 in 1, I will get Q is equal to Q1 plus, for Q2 I can write Q1 into capital R square by small r square. So Q1 comes out to be capital Q R square by R square plus capital R square. And similarly, Q2 can be calculated as Q1 capital R square by small r square. That means Q2 will be Q capital R square by R square plus capital R square. So I put the value of Q1 and Q2 here. We will be getting potential at the common center O 1 by 4 pi epsilon naught Q1 by R. So it will become Q small r by R square plus R square plus Q2 by R. So Q2 is Q capital R by R square plus R square. And thus we'll get the common center potential as 1 by 4 pi epsilon naught or Q, and here small r plus capital R, here small r square plus capital R square, like that. So this is the potential at common center. In this question, you have talked about the potential at center instead of earlier cases. You were talking about potential at this, potential at this. But now you have talked about potential at the common center.